Okay, we are going to take a look at the first part of topic 4.9. So this is in our mini unit on electrochemistry. We skipped 4.9 in unit 4, so we're bringing it up now, right? So this unit is all about oxidation reduction reactions. You can tell that's the title of this topic. And before we really explore those reactions in depth, we have to understand something called oxidation numbers. So an important idea to help recognize oxidation reduction reactions is to identify the oxidation number or oxidation state of an atom. The oxidation number is also called the, quote, apparent charge. So an example, I've got two chemicals written here. I've got an ionic compound, I've got a covalent compound, and all the elements are given charges. So those charges are their oxidation numbers or their apparent charge. So that's what we're going to learn how to identify, is what these charges are. Now, when we look at these belong to each individual element. So I've got one nitrogen with a +3. I've got 4 hydrogens, so each of those would be +1. And then the one chlorine would be -1. Here I've got a carbon that's -3, so each carbon would be -3, and then each of the 6 hydrogens would be +1. So again, we're going to learn how to identify those numbers and figure them out. So, atoms in ionic compounds have charges, and these are also their oxidation numbers. So we've seen charges before, we've seen oxidation numbers before, we just didn't call them that. But atoms in molecular compounds can also have oxidation numbers, although they do not have charges normally. Their oxidation numbers are assigned charges so that we as chemists can figure out which atoms have the electrons in a reaction. Oxidation numbers are written as something like +1 instead of like a charge, which is written as 1+. So we can see that difference. So we'll look at some examples of that. Now, we are going to take a look at this list of rules and applying them to find oxidation numbers for chemicals. I have added some other examples over here, some basic ones I wanted to do first, along with some of the ones below. So it would be a good idea to write these out, give some space in between, or you can write them as we do them for this part. So we're going to be assigning these oxidation numbers to elements. So we're going to start with just a couple of the rules I'm going to go over, and we'll look at some examples, and then we'll dive into all of the rest of the rules as we need them. Okay, so an element by itself is going to have an oxidation number of 0. So some examples of that would be like if I had chlorine, Cl2, magnesium by itself. Phosphorus comes in a set of 4 atoms. Oxygen comes as O2. But these are all single elements, right? They might be bonded to another atom of the same element, like these ones are, but it's all one element. It's in its elemental form, okay? All of those would be assigned an oxidation number of 0. And I personally always put a little cross through mine because I want to know the difference between an O and a 0. That's just a personal preference of mine. You don't have to do that, but we want to know what's an O and what's a 0. So they would all have an oxidation number of 0. Our group 1 elements are going to have, or actually I'm going to save that one. We're going to jump down here. Monatomic ions is equal to the ion charge. So monatomic means one atom, monatomic, mono meaning one, and an ion is something with a charge. So it's going to be equal to the ion charge. So like sodium's charge is always, oops, there's our bell. Okay, so sodium. So monatomic ions, their oxidation number is equal to their ion charge. So if sodium always has a +1 or 1+ charge, its oxidation number is going to be +1 or +1. Phosphorus has a 3- charge. It's always its ion charge, so its oxidation number would be, -3. Ignore that. And iron in this ion has a 2+ charge, so its charge, its oxidation number would be +2. Okay, so that's where this part up here written as +1 instead of a charge 1+. So I know in AP Chem, they're very lenient on this. You can write oxidation numbers and charges the same way with the positive or negative in front, but that's really what the difference is. So if you're used to seeing me write the number and then the charge, the plus or minus, that's why, because an oxidation number, it comes the other way. But they would never ding you on that, okay? But if we have an ion, its charge is the same as its oxidation number, so that simplifies that one. So those are two of our basic rules that make things pretty easy. If it's a group 1A element in a compound, okay, so these are, if they're basically, unless it's an element by itself, we're talking about things in compounds. So if it's a group 1A element like sodium and it's in a compound, it's going to be +1. If it's a group 2A element like magnesium and it's in a compound, it's going to be +2. We can see magnesium here is by itself, not in a compound, so it's 0. But if it was in a compound, for instance, we wrote MgO, then we'd write its charge from, it would be +2. So let's look at some of these compounds and start exploring the rest of this, these rules as we go. So we've got a compound here, NaCl, sodium and chlorine. So sodium is a group 1 element, so we can see that for group 1 elements, if they're in a compound, we're going to have an oxidation number of +1. So I'm just going to write that above our sodium. Okay, now chlorine's group 7A. It's got, it's a halogen. We've got halogens down here. They're usually -1 and positive when they're with oxygen. Well, it's not with oxygen. It's usually -1, so we can put that there. Now, what we can do to check this is one of our other rules. Down here it says the sum of the oxidation numbers for a neutral compound is 0. So this is a neutral compound. We see there is no charge written to start, right? All of these are neutral compounds. These 4, this is not neutral because it has a charge written. There will not be any hidden secret charges, okay? They're very upfront. If there's meant to be a charge, we write it. If there's not, we don't. So these are neutral compounds. The sum of them, so if we added these together, they should equal 0 if it's neutral. Well, if we add these together, we get 0. So those are correct. And that's another way that can help us when we don't have a rule for something to help us find the other element. So let's check this one over here. We got magnesium. Magnesium's in group 2A. It's an alkaline earth metal. So those are always +2, just like their regular charge. All right, let's look at O. We've got oxygen, and it does have a rule down here. Usually -2, but -1 in peroxide. This is hydrogen peroxide, like that stuff you use on like cuts and stuff. So if it's in a peroxide, if we have those, a peroxide means those O2s like that in a compound, then it'd be -1. But it's usually -2. So we can pretty much bet that this is going to be a -2. We can also see it's a neutral compound, so these should add up to 0. +2 and -2 give us 0. All right, so continuing using these rules, we've got CO. Well, carbon doesn't have a rule here at all. So we're going to go to the one that does, oxygen. Again, oxygen's usually -2 unless it's in a peroxide. This is not a peroxide, so oxygen's going to be -2. So therefore, if this has to add up to 0 because it's neutral, then carbon has to be +2 to let it add up to 0. Okay, they have to balance out with each other. All right, let's check another one. BH3. So boron does not have a rule, but hydrogen does. +1 with nonmetals, -1 with metals. So boron is on that kind of nonmetal side of it's a metalloid, but it's on that nonmetal side. It's on the right side of that stair-step line. So we're going to say that hydrogen's with a nonmetal. So hydrogens are going to be +1, each one of them. Now, we have more than one hydrogen. So when we're doing our math here, we have to incorporate that 3. So if I multiply that by 3, I'm going to do a little arrow up here, I have a total of +3. So that means my boron has to be -3 to add up to 0. Okay, now there's only one boron here, so boron's oxidation number is going to be -3. Okay, so -3 plus +3 gives us that neutral compound of 0. I have +3 because I have 3 hydrogens, each with a +1 oxidation number. So 3 times +1 gives me +3. making my boron -3. And I only have one boron here. So -3 divided by 1 gives me -3. So those are my oxidation numbers for boron and hydrogen. So let's apply that same idea again here. We've got calcium and carbon. So calcium's a group 2 metal, so we've got a rule for that. That's going to be +2. But we don't have a rule for carbon. Okay, well, calcium, there's only one of them. So that's going to be a total of +2 for that. But we need to add to it -2 to get us to add up to 0. Okay? There's 2 carbons here, so if I divide that by -2, 2 divided by -2 is going to give me -1. So each of my carbons here are -1 to give me that -2 total. Okay, so it's the total charge that we want to figure out to add up to 0, but we need to assign our oxidation number for each individual element. So the way that we can look at this, another kind of way to visualize, is I have a calcium and I have 2 carbons. The calcium is +2 and each of the carbons is a -1. That totals up to 0. Okay, so if that's an easier way for you to think about it that way. All right, now let's look at this one. This is our nitrate ion. This is our polyatomic ion. So there's another rule down here. It says the sum of the oxidation numbers for polyatomic ions is equal to the ion charge. So when I add these up, this needs to add up to -1 because that's my charge on my nitrate is a -1 charge. Okay, well, let's think about this. We've got nitrogen. That doesn't have a rule. We have oxygen, usually -2. But it's not in a peroxide. So we're going to say, okay, oxygen's -2. Now, there's 3 oxygens. So if I multiply 3 times -2, that gives me -6. So now we got to think about what -6 gives me -1. Okay? What -6 gives me -1? That would have to be a +5. 5 and -6, or 5 minus 6 is -1. Now, there's only one nitrogen, so I'm dividing this +5 by 1, so I just have +5 for my nitrogen. Okay, if there's only one of them, all that charge goes to that one element. Okay, so our nitrogen is +5, our oxygen is -2. Again, another way to visualize this one is you've got a nitrogen, that's +5, and you've got 3 oxygens that are -2. So that gives me -6 and +5, which adds up to a total of -1. Okay, so whichever way kind of helps you visualize it, that's what we want to use. So let's take a look at these other examples down here. Now that we've got some of the basic rules, let's look through our list and see if there's anything we haven't looked at yet. The halogens are usually a -1 unless they're with oxygen, they're going to be positive. I don't see an example of that, but let me come up with one. If we did, let's see. I guess if we just did this, we did ClO2, something like that. So oxygen would be -2, but there's 2 of them, so that's a total of you can't see my hand. So oxygen is -2. There's 2 of them, so it's a total of -4, so chlorine would have to be a +4 to go with that. Okay, so that's how we apply that. So we look at the oxygen first. If with all of these, something you might notice after a while is your negative charge is going to go to the more electronegative element, okay, the one that's going to pull those electrons more. So like our oxygens are all going to be negative here because they're more electronegative. Oxygen's more electronegative than carbon. Boron's more electronegative than hydrogen. That sort of thing. So that generally is going to help us figure this out too. Those more electronegative atoms are going to typically get that negative charge. Okay. So looking down here at our examples, we've got hydrogen. That is just one element. It's by itself. It's not combined with any other element, so that would be 0. I don't have space above it, so I'm going to write below on that one. I like to write them above it. Some people write it below like that. Some people will list them, and I've done that before. We'll list like the hydrogen and the oxygen and then list them next to it. That could be helpful as well, especially when we get into larger reactions. So maybe I'll do some examples like that too. So like this would be hydrogen is 0. Calcium, it's that monatomic ion, so it's equal to its ion charge, so positive 2. This has hydrogen and oxygen. We have a rule for hydrogen. It's positive 1 with nonmetals. Now there are 2 hydrogens, so that would be a total of positive 2. Okay, oxygen, though, also has a rule, so we really don't have to do the math for this. Oxygen is going to be usually negative 2, and that would give us that negative 2. That would add up to 0. So hydrogen is plus 1, oxygen is minus 2. Okay, so however you want to write it, either way is good. Iron, we got solid iron all by itself. It's in that elemental form, no charge written, so it's going to be 0. All right, here's another good example. Now, here's where we get to ones where we stop having a specific rule for everything. Now, we do have a halogen. We've got chlorine. Halogens are usually negative 1. So there's my negative 1. I've got 3 of them, so that gives me a total of negative 3. And it's neutral, so then I have to have positive 3 to go with it. So iron's going to be plus 3. So we could write Fe with a plus 3 and Cl with a minus 1. Remember, we're listing how much each chlorine is, not the total. We're not saying Cl is negative 3. It's each chlorine is a negative 1. Same thing with charges. Okay, now things start to get a little more interesting. We're going to start getting chemicals with 3 elements. Let's do a couple more 2 before we get into ones with 3. So we're going to scooch down here to the C2H6. So carbon doesn't have a rule, but hydrogen does. When it's with a nonmetal, it's going to be positive 1. So there are 6 of them, so that's a positive 6 total. Now this is a good one because they both have subscripts, so we're going to have to do a little more math here. So if this is going to add up to 0, then I need negative 6 with my positive 6 to add up to 0. Now, to get to my carbon, each carbon is going to split up that negative 6. So negative 6 divided by 2 is going to give me negative 3. So our carbon is negative 3 and our hydrogen is positive 1. Okay, we've got 2 carbons that are each negative 3 and 6 hydrogens that are positive 1. That gives us a total of 0. Okay, let's do this one over here, this manganese oxide. So we've got MnO2. We've got oxygen is usually negative 2 unless it's in a peroxide. So let me explain a peroxide because we see this O2 and we might think that this is a peroxide. A peroxide is meaning there's 1 oxygen for every 1 of the other element. Okay, so 2 hydrogens, 2 oxygens. There's 1 oxygen per hydrogen, so it's a peroxide. Okay, if this was Mn2O2, that would be a peroxide, but it's not. It's just MnO2, so oxygen's normal, negative 2. Okay, so we've got 2 of those. That's going to mean we have a total of negative 4. So manganese has to be positive 4 for this to add up to 0. And there's only 1 manganese, so it gets all of that positive 4. So Mn is positive 4, and oxygen are each negative 2. Okay, now let's look at some that have more than 1 element. Okay, I'm going to start with this NH4Cl just to kind of ease us into this. So nitrogen doesn't have a rule. Hydrogen does. It's positive 1 with nonmetals. Both of these are nonmetals. Chlorine's a halogen, usually negative 1 with nonmetals. So let's look at our math. We've got 4 hydrogens, so that gives us positive 4 from hydrogen. We've got 1 chlorine, so that's negative 1. This whole thing has to add up to 0. So +4 and -1 gives me +3, which means nitrogen has to be a -3 for this whole thing to add up to 0, right? We got +4, and then those two give us -4. We've got 1 nitrogen, so then all of that -3 charge goes to that 1 nitrogen. So my nitrogen is -3, my hydrogen is +1, my chlorine is -1. All right, let's do the same thing over here. Potassium is a group 1 metal, so it's going to be +1. Oxygen has a rule, it's not a peroxide, so it's going to be -2. So I've got 1 potassium, so that's a +1. We don't know manganese, and then I got 4 times -2, giving me -8 for oxygen. That has to add up to 0. So we've got a total of -8. We need a total of +8 over here to add up to 0. So I've already got +1. I need 7 more to give me that +8. So that means manganese is going to be a +7. So I got potassium is +1, manganese is +7, oxygen is -2 each. Potassium permanganate, favorite chemical. Okay. We can apply that same sort of thing down here on these two. Maybe try this one. Try your Na2CO3 by yourself. See if you can figure it out, and then pause and then come back and check it. Okay, hopefully you tried it. So sodium's group 1, it would be +1. Carbon, we don't have a rule. Oxygen would be -2. So then I've got 2 sodium, so it's going to be +2. I've got 3 oxygen, so it's going to be -6. And then I need to add something to those to get a total of 0. So I've got -6 plus, so I need this part to be negative, or to be +6. I've already got 2, so I need +4 to equal that out. That gives me my +6, my -6, that gives us 0. So carbon is going to be +4. So we got sodium is +1, carbon is +4, oxygen is -2. All right, this would be another good one to try out, K2CrO4. Try that one out. Pause and try it out. Let's check it. Okay, so potassium is a group 1 metal, so +1. Oxygen is always -2, unless it's in a peroxide. So we've got a little math to do. We got +2 total. 4 times -2 gives us -8. And this needs to add up to 0, and there's no charge written on that chemical. So what are we going to put there to make this a true statement? We got -8. We need a total of +8 over here to get it to be 0, so we need +6. There's only 1 chromium, so that whole charge goes to the chromium. So each potassium is +1, chromium is +6, oxygen is -2. All right, let's try one last one here, and I'll think about if there's anything else I need to show you. So hydrogen's got a rule, +1. Oxygen's got a rule, -2. We've got 1 hydrogen, so that's a +1. We've got 3 oxygen, so that's -6. We need something there for sulfur, and then this needs to add up to that charge. This needs to add up to -1. That's a little different. So we've got -6. So we need to balance it out with a +5 here, because 5 minus 6 gives us -1. So I've already got +1, so I need +4 to give me a total of 5 there. So this would be +4 for sulfur. So hydrogen is +1, sulfur is +4, oxygen are each -2. Right, so that's how we can figure out a polyatomic ion. We want it to add up to that charge, just like we did with the nitrate up here. Okay, trying to think if there's any others. If you come across something that seems a little odd, you're struggling with it, check to see if it's already an ionic compound. Sometimes they have things that don't have, both chemicals don't have rules. So maybe let's see, iron doesn't have a rule, and sulfur doesn't have a rule. So maybe I had FeS is my chemical. Neither of those have a rule on our list here. Well, it's a metal and a nonmetal. It's an ionic compound. They are going to follow their normal charges that they would normally have in that ionic compound. So sulfur always has a -2 charge, just like it would normally. Iron has a +2 in that case because it's neutral. So we would assign them their normal ion charges. So if you come across something that seems like you can't figure it out, think about if it's an ionic compound, is it metal and nonmetal. If it is, then they're going to follow their normal charges. Okay. Let me look through our practice and see if there's anything else that stands out to me. That might be a little more difficult. Possibly number 7. Let's look at number 7. So this part kind of bled through a little bit. That's okay. Okay, so the only thing in number 7 that has a rule is our oxygen. We know that we have oxygen, and it is -2. Okay, so we got to figure out nickel, nitrogen, and oxygen. But here's the deal. This nitrate ion, NO3, we already figured out. Nitrate is a +5 and a -2. Because that part, that polyatomic ion, has to add up to its ion charge. And the only way we can get that is if nitrogen's a +5 and oxygen's a -2 to get us that +1 charge. So no matter what the compound is, I don't care what we put nitrate with, the nitrogen's a +5 and the oxygen's a -2. So we can apply that here. If we think about the nitrates separately, knowing that fact, oxygen's -2, nitrogen's +5. Now, if we hadn't already figured that out, we could separate out that nitrate, look at that nitrate ion, just like here we can look at sulfate, and then we could apply those ones down here. Okay? Or we could apply that sulfate with this one. That sulfur is going to be the same no matter which chemical it is because it's still sulfate ion. So now that we know this information, we know that nitrogen is +5. Let's do some math. I've got 2 nitrogens because it multiplies through, so that gives me +10. I've got 6 oxygens. 6 times -2 is -12. This has to add up total to 0. So I've got -12, I need +12 to balance it out. So that would be a +2 charge for our nickel. So that gives me +2 here, +2 here. Another way to think about this is we know that the nitrate ion, if I was to take this chemical and separate it, I'd have nickel, and then I'd have 2 nitrates. This is again why we practice separating our ions out, a couple in unit 2. We know nitrate's negative, there's 2 of them, so nickel would have to be 2 positive. That's its normal ion charge. Therefore, its oxidation number is +2. So we can think about it in a couple of ways. If we already know nitrate, we can use that to help us find nickel, or we can use the regular ion charges to help us figure out nickel and then calculate nitrogen from there if you're not sure. So we've got multiple options. Always check though in like this one, calcium's in group 2. So we know that one, we know oxygen, we can calculate sulfur. Okay, so this is your practice on oxidation numbers. When you get into part 2 of this unit, you're going to be assigning oxidation numbers to chemical reactions to each element in the chemical reaction to see what happens to the charge as we go from the reactants to the products and see who's changing their charge, what's happening with those oxidation numbers. Okay, so that's where we're headed with this. All right, thanks guys.